Hello, this is Mridula and this is my Physics 2212 Lab 5 video, Faraday's Law. The purpose of this lab video is to study magnetic induction and eddy currents by analyzing observational data of a bar magnet falling through an aluminum tube, and to compare the observational model with the computational model in GlowScript. A preview of the main results are the experimental time was found to be 1.33 seconds, and the computational time was predicted to be 1.892 seconds. The principles used in this video are the Biot-Savart law, which is used to calculate the current generated by a current-carrying conductor. So the formula is dB is equal to nu naught I dl cross the unit vector divided by 4 pi r square. And then Faraday's law, which states that a changing magnetic field induces an electric field in a conductor. And finally, Newton's second law, which is the force on an object equals the rate of change of its momentum with respect to time. So the force vector is equal to the mass times acceleration. And then Newton's third law, which is for every action there's an equal and opposite reaction force. The system is the bar magnet and aluminum foil. The surroundings are everything else. So the initial conditions is when the bar magnet has not been dropped yet, so the velocity is 0. The mass of the magnet is 0.025 kg, length is 0.30 meters, width is 0.006 meters, and inner radius is 0.025 meters, and the magnetic dipole calculated from lab 4 is 6.398 A times m squared. So the procedure is to use the magnetometer app to find the north pole of the bar magnet, then to drop the magnet into the aluminum foil tube. Third step is to record the time it takes for the magnet to enter and exit the tube, and the final step is to repeat this process 5 times. So after 5 trials, the average time calculated was found to be 1.33 seconds. Next up are the initial conditions of the computational model. So nu naught is e to the power 7, resistivity of the aluminum tube is 2.65 e to the power 8, and then we have gravity, and the dimensions of the tube are given that we talked about earlier in the initial conditions, and the properties of the bar magnet. The mass of the magnet is 0.025 kgs, and the magnitude of the magnetic dipole moment is 6.398, which was calculated from lab 3. So in the first image, I declared functions to calculate the magnetic field of the magnet and the magnetic flux, and in the second image, I declare functions to take into account the forces acting on the bar magnet, so the magnetic force acting upwards and the gravitational force acting downwards, and then I find the net force by adding both those forces, and with the net force I use it to update the velocity and position using the velocity update formula and the position update formula, and then I print the time in tube in seconds taken for the bar magnet to fall through. These are the results of the computational model. So in the first picture, the intensity of the color indicates the magnitude of current flowing through the tube. So the red on top indicates anti-clockwise and the blue indicates clockwise, and the velocity time graph talks about the forces acting on the bar magnet. So in the beginning and end there are unbalanced forces acting, and in the middle balanced forces are acting. Next are the assumptions and sources of errors. So the assumptions I made where the air resistance is negligible, bar magnet acts as a magnetic dipole, and the only forces acting on the magnet are gravitational and magnetic. The errors I could have encountered are human error when using the stopwatch, incorrect dipole moment calculation from lab 4, and friction when the magnet hits the sides of the tube, slowing it down. Finally are the discussion questions. So the answer to the first question is a very low to no resistivity would produce a larger induced current, which produces a larger magnetic field and a greater opposing magnetic force. So as a result, the magnet would fall slower through the tube. To answer the second question, the holes would decrease the overall induced current in the tube, which decreases the magnetic force. As a result, the magnet would fall faster through the tube. Thank you.